So this video we're going to look at solving systems of linear equations. This is when you have two different equations and two variables, and you want to figure out what both of those values are. So which value of x and y will satisfy both of those equations at the same time. There are a lot of real-world examples that deal with this. You could have two scenarios where you're a business owner and you want to know, okay, I could make this have a base cost. If somebody wants to purchase this thing from me, I could have a base cost and then charge a certain amount per item, and I could change that and make it different ways. So if you wanted to compare two different plans, you could come up with two different equations to model those plans and then compare and see when they would be the same, at which point would you break even, that kind of thing. So we can, and you'll see some real world examples on that as well as in your discussion for this week. So what we're going to do is we're going to take two equations and we're going to consider it as a system of linear equations here. So what we're being told is that both of these things are true at the same time. So we need to figure out which value of x and y make both of these statements true. So what I'm going to do, I'm going to solve this using three different methods, not this particular one, but we're going to look at three different ways to solve. I'm going to solve this one in two ways. The first of these two ways is graphing and substitution. So graphing, what we want to do, these are both in slope-intercept form, so they're kind of easy to graph by just finding the slope and the y-intercept. So the slope here is 3/2 and the y-intercept is 1. And then on this one, and I covered this in the last video, if you want a review of that. But the slope on this one is -1. There's understood to be a 1 there, so that's -1, and the y-intercept is 6. Again, with slope, it's rise over run, so we want to look at this as a fraction, so I'm just going to put that over 1. It's understood to be over 1. Okay, so I'm going to graph both of these, and what I'm looking for when I'm solving a system, now when you think about two lines, every point on that line is a solution to that equation. So the one point where that's a solution to both lines is where they intersect. So what I'm looking for is the point where these two lines will intersect. And that will be the one point that satisfies both of those equations. So I'm going to start with graphing this one. I have b equals 1, so that's right here, the y-intercept on the y-axis. And then my slope is 3/2, so I'm going to go up 1, 2, 3, and run 2. So rise is 3, run is 2, and that's my point. Now, on this, we only need 2 points to graph a line, but I'm going to keep going just because I want to make sure that I kind of have enough points to be able to see this. In Alex, you won't necessarily need to do that. You'll be able to see it pretty well, but you'll see kind of what I mean here. But I'm going to keep going. My slope is going to be constant, so I'm going to keep going up 1, 2, 3, and over 1, like that. So I think I have enough at this point that I'm going to go ahead and connect those points. And then I'm going to move to this other line and see where these lines intersect. So this one has a y-intercept of 6. So I'm going to go up to 1, 2, 3, 4, 5, 6 here. And then the slope is -1 over 1. So I'm going to go down 1 since it's a negative slope. So from there, I'm going to go down 1. Whoops, I don't want to plot yet. Down 1 and to the right 1. And then again, I'm going to do that again just so I can kind of get more points and see where these might intersect. So down 1, over 1. And it falls right on top of that other point. So every point on this line is a solution to that equation. Every point on that line is a solution to that equation. The one point where they intersect, that is a solution to both. So that is a solution to both, and that point is 2, and then we went up 1, 2, 3, 4. So the point 2, 4 is our solution to that. So that is the answer to that problem. It is possible for, if you have two lines that are parallel, which would mean they have the same slope, then in that case they don't intersect, so there's no solution. And then in some cases you might have one line that falls directly on top of the other one. And in that case, they intersect everywhere, which would be infinitely many solutions since those lines go on forever. So those are different scenarios for that. So that's graphing. to solve systems of linear equations. That's one method, especially if they're in slope-intercept form. That can be a very useful thing. Also, like I mentioned with modeling, sometimes it's good to see a graphic model of how two different scenarios would relate. So we could see kind of what's happening with this scenario, what's happening with that scenario leading up to that point, and then what the intersection means. And we'll talk more about that in our discussions. Okay, so I want to solve this also using systems of, solve the system of linear equations using this method, the substitution method. So this is graphically, this is the first method. The second method is using substitution. I'm going to show you a little bit more involved problem on using substitution as well, but on this one, it lends itself well. Substitution means that you solve one equation for one variable. And then you simply plug that expression into the other equation. Okay, so on this one, these are actually both already solved for y. So this is going to be pretty straightforward. I can use either one of these, but if I look at this as y equals negative x plus 6, this whole thing is what y is equal to. So I can just take that and plug it in for the y in the other equation. Since I know that both of these are true at the same time, I know that y is equal to this and y is equal to that. So that means that this expression must be equal to that expression. So I'm just going to set that up as 3/2 x plus 1 equals negative x plus 6. And then I have an equation that I can solve. For x, it's only one variable now, and that's the problem. When you see it graphically, you can find two, the ordered pair, which is the x and the y value. When you're solving using substitution, you notice that there are two variables here that we need to solve for, but we only know algebraically how to solve for one of those. So we get it down to where it's only one variable, and then we can isolate that variable and solve. In this case, I need to get x by itself on one side, so I'm going to add x to both sides. 3/2 x plus x is 5/2 x. Plus 1 equals, those canceled, equals 6. And then I'm going to subtract 1 to get 5/2 x by itself equals 5. I'm going to take this up here. I'm running out of room. So 5/2 x equals 5. To get rid of this, I mentioned in another video to eliminate, when you're solving an equation, if you want to get rid of that fraction, you can just multiply by its reciprocal. So I'm going to multiply by its reciprocal because multiplying reciprocals always equals 1. So if I do that on one side, I've got to do it on the other side. So over here, the reason those cancel, they'll just cancel out. They're like the numerators cancel and the denominators cancel. Equal 1. And then over here, that's 5 times 2/5 is just going to be 2. So that's going to give me x equals 2. You'll notice that up here, x also equals 2. So then what I need to do, once I have one, I just need to plug back in here to solve for the other. So solving for y, I'm just going to take this 2 and plug it into either one of these. This looks nicer just because it doesn't have fractions. So I have y equals negative x plus 6. It does not matter which of these two equations you plug it back into. That's going to be y equals negative 2 because there's a negative in front of that x, which again is like a negative 1 times x. So it's going to be negative 2 plus 6, which is 4. And so our solution, x was 2, y is 4, and that is the same thing we got when we did this graphically. So you can see that when you have it in slope-intercept form, graphically and using substitution are both pretty straightforward. I'm going to show you now an example of a substitution problem that's a little bit more involved. Since we won't have y solved for. And this is actually, substitution is handy when you have these in what's called standard form. And both of these equations are going to be, actually one of them is in standard form. We have y equals 3x plus 8 and 5x plus 2y equals 5. All right, this is standard form where you have ax plus by equals c is standard form. If you have one, even one or both equations in this form, then substitution is probably going to be your best bet for solving. Now notice this one's already solved for y, and the first step was solve one equation for one variable. There will be situations where you don't have it solved for y. So you would need to solve one of the two equations for one variable. It could be x or y. You just want to get one variable by itself in one of the equations. In this case, I have this y equals 3x plus 8. So what I'm going to do, since I know that y is equal to that, and that both of these things are true at the same time, then I know that this y must be equal to 3x plus 8 as well. So I'm just going to take that expression, 3x plus 8, and plug it directly in for this equation. So I have 5x plus 2 times 3x plus 8 equals 5. So it's exactly this equation except for where I saw y. Now I see this 3x plus 8 because I know that y is equal to that. So I am going to then just solve by simplifying on the left side first. I need to use the distributive property. 5x plus 6x plus 16 equals 5. And then simplifying further over here, I've got some like terms. 5x plus 6x is 11x plus 16 equals 5. And then I'm going to subtract 16 from both sides to continue to solve. And I'll get 11x equals negative 11. And then dividing by 11 to further solve to get x by itself. Oops, help if I would divide by 11. So divide by 11, and that cancels, and I get x equals negative 11 divided by 11 is negative 1. So I get that value of x. I need to solve for the y value, then I'm looking for the ordered pair that satisfies both of these equations. Now that I have x, I can just go back into either one of these two equations and plug in to solve for y. In this case, it's a lot easier to just go back and plug it in here, and I could almost just go back up here and plug in. I know that y is equal to 3 times x, which is now known to be negative 1. And that's 3 times negative 1 is negative 3, plus 8 is 5. And that is your y value. So my order here is negative 1, 5. I mentioned when we were dealing with just solving equations that it's always a good idea to go back and plug this in to make sure that it works for both equations. So I do encourage you to do that. I'm going to do that verbally just quickly here. But I encourage you to plug these back in and make sure that they actually work. If they don't, you know something went wrong. So we have a negative 1 for here and a 5 for this y. So 3 times negative 1 is negative 3 plus 8 is indeed 5. And we kind of just saw that there. We'll plug this in here too as well. 5 times negative 1 would be negative 5, and then plus 2 times 5 would be 10, and that does, negative 5 plus 10 does indeed equal 5. So we can do a quick check there to know that we got the right answer. And I would encourage you to do that for all of these problems. Okay, so the last part is to solve for systems using elimination method. If both, I mentioned earlier that if both or one are in standard form, that substitution may make sense. There's one that makes it even easier than substitution, and that would be elimination. So here's an example of elimination where we have 2x plus 5y. And I think I may have actually misspoke earlier. I think I said that when they're both in this form that substitution was the easiest, but elimination is actually the easiest when they're both in standard form. If one of them or none of them are in standard form, if they're solved for a variable already, then substitution will be easiest. This one wouldn't be terrible to do substitution because you could pretty easily solve for this x, get this x by itself. And if you did that, then that new expression that you solved for x, you would just plug that into this x and solve from there. But I'm going to show you how to do this using elimination. Elimination is basically where you're going to add, this is also called addition method, so you're going to add the two equations together so that one of the variables cancels out. But the only way that you can do that is if they're opposites. So for example, if I want to add these two equations together, here, if I'm looking at the x's, and it could be either variable that I want to eliminate, but I'm going to look at x in this particular case. The opposite of 2x would be negative 2x. So if this was a negative 2x, when I add these two equations together, these would cancel out. So that's kind of the goal here, is I want to get this down to one variable, an equation that is in one variable that I can solve. So if I just add these together right now, it'd be 3x plus 3y equals 15. That's not helpful because I still have two variables I can't solve. But if I can get one of these variables to kind of disappear, eliminate it, then I'll be left with one variable and can solve. So what I'm going to do is I'm going to change this so that it is the opposite of this. And I could do the same with the y's, but I'm going to, again, you can kind of learn, you'll look at some strategies on this throughout this lesson. But the opposite of 2x is a negative 2x, so I'm going to make this a negative 2x, but I can't just change that without changing the entire equation. But I do know that I can keep a balanced equation if I do something on one side and do it to the other side. So what I'm going to do is I'm going to multiply this entire equation by negative 2, because that's what I want to multiply this by. It could be opposite of this 2x. So, but if I do it there, then I have to do it to everything. So I'm going to rewrite this whole equation now, so that I have these opposites. So I'm going to rewrite that first one. And then I'm going to take this negative 2 and multiply it straight across. So I've got negative 2x plus 4y equals positive 8. And now, again, this is sometimes called addition method. I'm going to add these two equations together, add the x's, add the y's, add the constant terms together. This will only work, by the way, if they are both in the same form. You have to have the equal sign lined up, the x is on the same side of the equation, the y is on the same side of the equation. It needs to be set up this way. So I'm going to add these together. 2x minus 2x, those cancel, so eliminating those. 5y plus 4y is 9y equals 19 plus 8 is 27. And then look how easy that was. I got opposites, one of them canceled out, and that is super straightforward to solve. I just divide by 9 on each side and I get y equals 3. Well, just like the other method, substitution, once you get one variable, we do need to take it back and plug in to solve for the other variable. It does not matter which equation to plug it into to determine that. I think this one looks a little bit easier, but again, that's up for your, you can plug it in either one of these to figure out what the x is. So I'm going to take this up here to figure out what x is and plug it in this one. So x minus 2y equals negative 4. Y we just learned is 3. So x minus 2 times 3 equals negative 4. Negative 2 times 3 is negative 6. So I've got x minus 6 equals negative 4. And then I'm going to add that 6 to both sides to solve. And I'll get x equals 2. So I get 2 for x and 3 for y. And again, I can plug this in. 2 times 2 is 4, plus 5 times 3 is 15. 4 plus 15 is indeed 19. And I can plug in here 2 minus 2 times 3, which is 6. So 2 minus 6 equals negative 4. And I know I'm doing that quickly, but if you want to practice, try plugging that in to make sure. I always like to go back and check just to make sure it's right. So that is our answer to that problem. So that is elimination. I'm going to show you one more example of this, and then that will be it for this entire module. Okay, so this last example, we have 3x plus 4y equals 10, and 2x plus 3y equals 7. All right, so if you consider which method to use to solve this, graphing, kind of messy potentially. Substitution, you have a lot going on here. If you wanted to solve this one in particular, or really both of them, to try to isolate one of these variables, you're going to end up with fractions. It could be kind of messy. But elimination, this is where elimination comes in really, it is really useful. You have two that are in standard form. We're going to get those opposites like we did in that last one, where we can cancel, eliminate one of those variables and get it down to one variable. This one is not as obvious as the last one. We had 2x, the opposite of 2x was negative 2x. That's pretty easy to figure out. This is not as easy. The opposite of 3x is negative 3x. There's not a nice, easy way at least integer value that we can multiply by 2 to make it equal to -3. So we're going to have to get a little bit more creative, and this is where least common denominator comes in. We're going to look for the least common denominator, least common multiple, which is the smallest number that will divide both of these, and we're going to try to get those opposites. So if you think about these, the least common multiple for these is 6. 6 divides 3 evenly, 6 divides 2 evenly. We could also look at these. 12 would be the LCM for these, and we could get 12 and -12. But since this is just a smaller number, I'm going to do it with these. So what I'm going to do is I'm going to try to get this to be a 6x and this one to be a -6x. I could do reverse. I could do -6x and +6x. But I want them to be opposites. That's the goal. So again, like the other problem, whatever I multiply this by, I need to multiply the entire equation by that value. And again, I want opposites. That's the goal. I want one of these variables to be eliminated. So I'm going to make this a 6x. What I'll multiply 3x by to get 6, I multiply by 2. So I'm going to multiply the entire equation by 2. Now, if that's 6x, I need this to be -6x. So I'm going to multiply this by -3. Again, multiply by everything. So I'm going to bring this down. 2 times 3x would be 6x. 2 times 4y would be 8y. And 2 times 10 would be 20. Word of caution, the biggest mistake I see with the elimination method is forgetting to multiply all the way across, even on the other side of the equation. So make sure that you are multiplying that by every term in that equation. And then this one we have -3 times 2x is -6x. -3 times 3y is -9y. Equals -3 times 7 is -21. Now I've got opposites, so I'm going to go ahead and add. Those cancel out. 8y minus 9y is -y. Equals 20 minus 21 would be -1. And I'm almost done solving for y. I just need to divide. That's like a -1 there, so I just need to divide by -1. And I will get y equals 1. And once I've got the y value, I just need to go back and plug in to find the x value. Again, you can plug in either of these two equations to find the x. I'll just pick the first one just because. So 3x plus 4y equals 10. I'm going to take this y equals 1, plug that 1 in there. So 3x plus 4 times 1 equals 10. 3x plus 4 equals 10. And then I'm solving, subtract 4 from both sides. I have 3x equals 6. And then to solve, just divide by 3 on both sides. And you will get x equals 2. So your solution, you got 2 for x and 1 for y, and that's your solution. And again, we could go back and plug that in, and I'll always encourage you to do that to make sure that it worked. So that is systems of linear equations. And as always, if you have questions on any of the problems that you're working on in ALEX, please shoot me an email or post to the general discussion board, and I'll be happy to help you. All right.